multiple mutual peers. Actually, we're doing this research from a single mutual peers to the multiple mutual peers. But it will be very complicated for this research. So the outline of this presentation is divided by 6 parts. So the first one will be brief introduction, what we're doing about this research, and what is the application for the future construction. And the other one will be the acting principle of the NEM of the mutual peers. I want to go through about the concept of these new ideas. Then the third part will be the modeling for a bridge with multiple NEMs. Actually, it's from the single mutual peers to the multiple mutual peers. We should consider that we're using an active control methods. Then the other one, the control laws of these proposed methods should be detected. On the other hand, the interaction between the different NEMs should be considered. So the first part we will go through about the test setup. Actually, we're using about get controller, so I want to go through about the experimental parameters. It will be discussions about parameters. The different control parameters will use about different control effects. So we should consider about this one. Then the first part we will go through about the test result and the discussions. Finally, we will give the brief conclusions. Actually, Taiwan is located in the Pacific Rim, seismic range, with the poor geological conditions. Actually, Professor Lee was considered about this Taiwan is not very good at geological conditions, so we will use about it. If it's stricken by the strong earthquake and typhoon, they will lose the mountain soils and accuse about the debris flows, such as the double debris flows, resulting in bridge damage and canal effects. Therefore, the rapid development of disaster relief and the post-rehabilitations are affected tremendously. Actually, according to the global warming, so the intensity of the natural disasters such as earthquake, mudslides, and slowland collapse has increased significantly. When such a disaster occurs, the rescue equipment and supplies cannot be fast arrived in this disaster area in the short possible time to save their lives. So if the bridge is damaged, the rescues cannot reach to the disaster area, so the relief systems will be delayed. Therefore, the lightweight of the bridge for disaster relief systems is very important component of the disaster relief systems. However, the reductions of the lightweight bridge is restricted by the available space at the site, support conditions, and other factors in the area of the damaged bridge. Thus, the currently available structural system operation cannot be applied to all disaster sites. So I want to show you all the videos that will be happening on the north of the Taiwan operation maps. Actually, it's happened on October 2019. So you can see this video here. And you can find the heavy truck path through about this center of the bridge. And the steel tendons about this one will be loose detention force, and it will be cut. It will accuse about the collapse of this bridge. So you can see here is those days tension force. But if we can use our methods at the center of the bridge, then you will keep the stable of this bridge, then it will be stable of our lives. So you can see here, if we use our methods at the center of the bridge, and you will keep the stable of the bridge to avoid this collapse of the bridge. So in our previous research experiment that shows the if installed on the bridge can act as the mutual peers, which can reduce our vertical displacement and the section stress effectively. Although this effect of spans of the bridge can be increased, we start increasing our depth of cross sections. We see we must extend our next span of bridge, so the cross section of the depth of the cross section should be increased. But in this one, we don't need to increase about the cross section of the depth of the cross sections. Therefore, in order to extend the next span of bridge to increase the flexibility of the different land modification, this study installed the multiple NEMs on bridge to provide the multiple mutual peers. But use this technology, we should consider about 3 conditions. The first one is the controller must continue monitoring the bridge, the change of the vertical displacement of the bridge. Actually, this is moving on, that's not a constant load. So moving on will be moving pass through about the bridge, so we will consider that. Other the second one will be considered about the multiple NEMs calculate. Each of the NEMs should be calculated to target the angles of the rotation arm to provide appropriate uplink force, balance about the moving load. Then the third one, the control load, active control measures and the interaction between the multiple NEMs should be confirmed in this study. Actually, the control loads and the active control measures and the interaction behavior between the multiple NEMs should be tested to verify the control effect. Then this study we detected about the active control measures and the control loads of applying from the single degree, the single mutual Piers up to the multiple mutual Piers. Then there, in our study, we just install about 2 sets of the NEMs installed in this bridge, then which will reduce the vertical displacement. The performance was tested with the round trip test. Then it's used the dynamic test to verify the correctness of the active control load and the interaction behavior between these 2 NEMs. So the vertical displacement of the mutual Piers with and without NEMs controller compared to explore the display control effect. This study. Otherwise, in order to detect the vertical displacement, in our research, we just using the display imaging correlation methods applied to detect the vertical displacement in these studies. So the part 2, I want to brief introductions about this NEM concept. So you can see here, this is the video. On the left-hand side is the bridge response control. On the right-hand side is the bridge with control. So you can see there's the rotation arm here. It will be changed to the suitable angles to provide the appropriate uplifting force to balance about this moving load. So you can see here, the deck of the bridge is standard stables. So in this study, I want to show you about this slide. I want to explain about this detail. Actually, there's a set of seismic rotation here. It will be including about the spin, arms, gear measuring, motor, and motor controller. Then there will be arcing set here. It will be arced for the steel tenders. The steel tenders should be mirror-like. Actually, we will be even number of the steel tenders. Actually, this steel tenders is used to offset the horizontal direction force and produce about uplift force to balance the vertical displacement that was used by the moving load. Then the other one, there's the displacement sensor. We use the potentiometers to detect about the vertical displacement. Actually, this sensor will be detected about the signals of the displacement variations. They will be changed. They will be sent to we use the MPU 90 to 50 process. Then you will be calculate about the vertical displacement variations. Then you will be changed to send the signals to the Arduino layers. They will be changed to sent to the RC server to rotate about the rotation angle to provide the suitable uplift force. So this one will be a difference with discussion about this one will be just with the one visual Piers using only one NEMs. Then the other one we can install many NEMs on the bridge. Therefore, the lifespan can expand. But all the cross section is the same. It's no difference between the single NEMs with the multiple NEMs. But there's many elements installed on the bridge we should consider about different variations. So the rotation angle is different at each position of the NEMs. So I want to discussion about this concept, how we provide the uplift force. I just mentioned there's a hole on the cantilever hole here, cantilever arms here. Then the steel tendon just passing through about the position of this hole. Then you will be arced at the end of the arch end. Then you will be provided about a single angle of theta. So then the thetas will be Q's about the resultant force R is equal to 2t times sin theta. On the other hand, in this research, we just use the vertical displacement signal detected by the potentiometers. They will be sent to the microcontroller unit, which will be ordered the RC server to rotate the cantilever arms to the suitable angles to produce about upward force to balance about the moving load. Actually, these rotational arms can be rotation from the horizontal to the vertical of this bridge length. So I want to use this slide to show you how we change about this one. So you can find this is the maximum upward force when the rotation angle goes up to the 90 degrees. Then you will be changing it. This is small one. There is no moving load on the bridge, so there will be stable on the horizontals. Actually, in this vertical displacement at the NEMs installation positions, we can find all the vertical displacement remains zeros. Then the strain energy should be stored in the steel tendons. The steel remains constant. So there is no strain energy difference in the steel tendons. Then we'll go through about the modeling for the bridge with the multiple NEMs. Actually, the NEMs can operate with the very small energy supplies to generate a great deal of control force to counteract the displacement effect of the external on the bridge in order to achieve automatic controls as well as the displacement control at the installation position to stable at zeros. So the controller of each NEM should be continuously monitor the displacement change at its installation positions. So we use this equation to explain what is our idea. So this is the rigid body motion for the equation motions. We use a single degree of freedom. So you can see here, N is the mass of the bridge, and C is the damping coefficient for the bridge. The K is the stiffness for the bridge. Then the PT is external force. It will be used by the earthquake force and the moving load. The other ones we call it external force. Then the UT is the control force. So control force must to balance about the external force. So you can see here, the PT minus UT should be equal to 0 to stable about this vertical displacement of this bridge. Actually, in our research, we just using about the linear control rules is used in the corporation control games. Then the TI is the control coefficient of the individual items. So and the third one will be the gain coefficient of the velocity. So the XT is the displacement function at each position of the installed with the NEMs. So T is respective about the time. So about this equation, we can easy to find. Actually, control force is just control from the Y, sine Y. Therefore, we should consider about this equation in our studies. So in our study, we just use these equations. Therefore, in order to simplify about our control methods, so we use the distress control systems. Therefore, this equation can be written as this equation. So the GP times displacement plus the GI times summation of displacement plus the GT times the velocity. So therefore, this the previous the slide just show you about the for single NEMs. But if we install it with the multiple NEMs, so we should consider about the process distributed cycle by cycle. Actually, the cycle by cycle, so we should consider different position of NEMs. Therefore, each different position with the NX should consider about vertical displacement. We call it a downward displacement detected by the potential meters. And the potential meters we can find here. This is delta Y Ki. So I is the respective number of I's NX, and K will stand about K steps. The different K steps we will provide about different vertical displacement. Therefore, we send to this equation calculates about the theta Ki. Then the theta K will rotation about the different rotation angles different. Therefore, the different NEMs provide the different rotation angle to provide the different uplifting force. Therefore, we can detect about moving load the position to provide uplifting force to balance about vertical displacement. So then I want to show you about the test setup and explain some experimental parameters that we do in our research. So when this one, we should consider about the control conditions, which is signal detections, control calculation, and predictions about mechanism movement as quite complicated. Therefore, we must confirm through dynamic test. So the purpose of dynamic test in this study was to verify the feasibility of the NEMs to form us about the mutual Piers of bridge. Therefore, the deformation control effect on the bridge equivalent with the model NEMs should be tested with the moving load. Actually, in our test, we're just doing about each of our two sets on this bridge. Almost the same. I just mentioned before about each set is the same. All the equivalent is the same. But it should be we should be considered about detection behavior between these two NEMs. So therefore, this one will be I just want to brief introduction about experimental frameworks of over-reduced scales of the bridge. Actually, we got some funding from the Minister of Science and Technology. So we can just using about the reduced scale bridge to test it. So you can see here, this is bridge test, and this one is moving load. We just use the vehicles. And this one will be the steel tendons. There's the different steel tendons is attached to this band of the bridge. Then it will be a two installed with the two NEMs at 1/3 and 2/3 of this bridge. Then this one will be potentiometers installed at the position with the NEMs to detect about this vertical displacement variations. Therefore, in our study, so this I want to brief introduction. In our research, we're just using about the DIC methods. We call it digital imaging correlation methods. So you can find this is the structure sparkle on the back of the bridge. So we can detect it to calculate about the vertical displacement variations. And this DIC methods, we just done this research about 15 years ago. We're doing about 10 years. So we got many powerful programs to analyze it. So this is the idea. So we can detect using the CCD camera. Then we can find this is before deformation, this is after the deformation, then we send it to the computer to calculate. Actually, this method is basically taken as the foundation of research progress mathematical calculation, compare the partial relative of two images. Actually, this is just considered of partial difference partial relativity of two images. We don't need to consider the whole structures. We just need to consider some parts of this bridge. Then we judge this image towards the reflection before after transformation. Actually, we can see this one. This is before deformation. This is after deformation. Therefore, if we can see in this image, the image A is the before deformation and the image B is the after deformation. Therefore, we set into the correlation function to calculate the difference between these two images. Therefore, we use this slide to explain this idea. Actually, the comparison of the local relation with these two images. Actually, this is based on the finite methods. So you can find this is sampling rate. We use a very small match to divide it. Therefore, there's undeformed sub-image. This will be two nodes, P and Q. Then this is the deformed sub-image, the P star and Q star. So it will be changing from the undeformation to the deformation images. Therefore, we use this equation. This equation will be easy to detect. So this will be after deformation, this one will be before deformation, and we will calculate the difference between these two images. So therefore, we're using this imaging correlation function to determine the degree of similarity. So you can see here it's very easy to detect. Actually, this GI is the dimension A before deformation and coordinate IAJ. Then the GIJ theta will be the dimension after transformation. So you can see here is the coordinate I bar and J bar. Then we compare with each other to calculate about the degree of similarity. So actually, this dimension calculation function of every sub-dimensions will be optimized to find the highest correlation values. So the corresponding coordinate of sub-dimension after deformation can be found out. Therefore, we can calculate about the displacement at every node using the coordinates before and after deformation. Then the full displacement field can be established. Actually, the full displacement can be calculated. Therefore, we can calculate and record about the history of the vertical displacement variations very easily. So therefore, I want to show you about the first part before we go through about experimental result and discussions about our research. So this is our test result. You can see here. This is with the low speed without control, and this is low speed with a small control gain, just a small control gain. The three different control gains. Just mentioned the GP, GT, and GI. Then with this one will be with the medium control gains, and this one will be with the large control gains. So you can easy to find. There's no difference between all these test result, but there are some things happen on the low speed with the large control gains. Actually, this will be used by the large control gains with high frequency vibrations when the accelerations of the moving lot. Therefore, we're using about the test for the high speed dynamic test. Actually, we're doing the same gains. This is without the control, with the low control gains, with the medium control gain, with large control gains. I want to mention this is the red line is for the installation position at 1/3 of the bridge, and this blue line is at the 2/3 of this position of the bridge. Therefore, we compare with each other, and then we can find the control effect is strongly affected by the control gains. Therefore, the large control gains, we can get the better control effect. But this is for high speed dynamic test. But with the low speed control, it should be the low control gains will be get control effect. Then we test it using the high speed test. So we're using about more heavy vehicles. So we added more mass on the vehicles to test it. I want to try to find some difference between the test results. So you can see here the orange line is for the 1/3, and the blue line is for the 2/3, the installation with the NEMs. So you can find the reduction rate, the displacement at the 1/3 span is up to the 98.5%. It's very perfect control effect. Therefore, I want to show you about the displacement control effect at the center of the bridge. There's without the NEM installation with the bridge. So, but you can see here, actually with the more heavy vehicles with the large control gains, the reduction rate at the center of the bridge is still up to the 95.6%. So I think this will be perfect about control effect for the bridge with the N1.NMs. So therefore, I want to show the video. Stage 1 will be the up one will be without control, and this one will be with the control. So you can see here the NEMs can rotate to a different angle to the right. After different force variance about vertical displacement is reduced by the moving load. So you can easily detect about from this video to show in these slides. Then on the other hand, I want to show you about the test result which use about DIC methods to detect about distable and vertical displacement of the bridge with the moving load. So you can see here it's very funny about this research. Now this one will be a bridge without control, so you can find there's cues about large vertical displacement of bridge when the is moving through the bridge. Then the other one will be controlled with the NEMs. So you can see here, vertical bridge has been controlled well. So we compare with each other, we can easily to find the difference with control and without control. That we're using about IDS methods. So therefore, we comparison of the maximum vertical displacement of the bridge with and without control. Actually, we use the heavy, I just mentioned we use the heavy vehicles. So we can see here, this is outbound trip, this is return trip. So there's reducing rate, we can find here. All the displacement control up to more than 93.3%. I think for the bridges control, control is very, very rare. Therefore, if we install our vertical elements for a bridge, then we can extend the lifespan of the bridge. So never mind, we can install 2, 3, or 4 elements with the bridge for the extended or the lifespan of the bridge. So therefore, I want to give a brief conclusion of my research. So these two items are rotated to survey load to provide the operator control force to reduce the vertical displacement, which was used by the moving load. From our video, we just showed you about the PID controller and brake-sensitive controller that can deliver to rotated to appropriate angle to provide the apparent application force to offset the moving load. Actually, we can see here, there's no big difference for the vertical displacement in here in our test. From the time history of displacement variations, and 1/3 midpoint and 2/3 point of the bridge under control NEMs that the vertical displacement are controlled that far below 1/4,000 over the next span of the bridge. Actually, this will be required by design criteria. So the vertical displacement is far below this value. So therefore, our methods is very useful. Therefore, this experimental confirms this NEM can be applied as the multiple mutual Piers of a bridge. And then the interaction between interactional behavior of this multiple tests we can find, it will be controlled well. Then this study we just confirms about the possibility of applying NEM to focus on multiple Piers, visual Piers of bridge. Thereby, we want to extend our research. Actually, we can control the displacement at any moment of the bridge well. So therefore, in our future study, actually we just wait for the funding from the Minister of Science and Technology this year. I hope they can give us some funding to do our research. We try to extend from the reduced scale to the full scale bridge. We just want to extend it to the 5 meter, 10 meter, and 50 meters bridge with the real full scale test. Then we can install the 1 NM, 2 NM, and 3 NM to test this result. Otherwise, with the control methods, we want to try to use the open loops and the closed loop controller to compare with the control effects. Actually, we can extend the VIP controller to the other control methods. Okay, thank you for your kind attention.